In this segment, we'll look at the ARM branch, right there, and multiply long instruction formats. And we'll revisit the way fixed bits are cleverly used to identify instruction formats. The branch instruction format is one of the simplest in the table, right there. And it has still several interesting points. After the cond, it has fixed bits 101, and then a single bit to indicate if the LR register should be set, making it a BL. After that, there's just the 24-bit offset. And the branch instructions we saw in our code examples always had a label representing an address as a target, but as we've seen over and over, it's not possible to store a 32-bit address in an instruction along with opcodes, condition codes, etc. Branches thus use PC relative addressing, just like LDR and STR, jumping to a location a given number of bytes before or after the current PC. However, their offset is considerably larger at 24 bits. Now, a 24-bit signed integer ranges from less than -8 million to over 8 million, which is a pretty large range of instructions before or after the PC. But the range is even longer than that. The offset is really a 26-bit offset because the CPU automatically adds 2 0 bits to the right end of it. And the first question in the lecture segment here is, why does it make sense to append 00 to the end of the offset? Isn't it possible that the desired offset might end with 01 or 10? Explain your answer. And the answer is that instructions are all 4 bytes long, without exception. So we would only jump by values divisible by 4. And those always have 00 as their last 2 bytes. So the 00 may as well be assumed. Another way to look at it is that the offset is in units of words, not bytes. To get a byte offset, we shift left by 2 bits, filling in with 00. And with this boost, the range of branch offsets becomes better than -32 million to +32 million bytes, or -8 million to 8 million instructions. So one can jump from one instruction to any other instruction, forward or backward, in a code block of over 8 million instructions. In some rare cases, we might want to jump even further than that. How would we do so? This is question 2. And there's a hint, we wouldn't use a branch instruction. We need to be able to jump to an address specified in a full 32-bit register. Well, the answer is that we'd load the desired address into, say, R0, and then we'd do a move PC R0. Or you could really save a step and just say, do a LDR PC some address, like that. Now, we used mul and mul A in an early example. Those are represented by these formats here, the top format, multiply format there. Let's see how those instructions are organized. In most tables, they're just under the data processing line, as you see here. And they are under multiply, not multiply long. The mul instruction has 6 fixed bits. All 6 are zeros to identify it. It has just 2 1-bit flags, an A and an S. And it has 4 register fields. And there, and there, and there. Plus more fixed bits in positions 4 through 7 here. It performs the operation RD equals RM times RS. But the same instruction provides the same format, provides the MLA instruction. Set the A bit to 1, over here, that guy, and then the instruction performs RD equals RM times RS plus RN. And if you want to set condition codes based on the result, you set the S flag, just as for data processing instructions. Question 3. Recall that mul does not allow a constant operand, only registers. Explain why this restriction is needed. And the answer is that the instruction doesn't offer any place to specify a constant. Everything is already taken up, all the bits are taken up by fixed bits and by specifying up to 4 registers. This proves to be less of an inconvenience than it might seem because multiplication by any reasonably small constant is usually done instead by addition and shifts, as we'll find in the module on optimization later on. Now, we did not use the multiply long instruction format. The assembly language MULL would get us that, but it's worth discussing since we're on the topic. This instruction computes Rn times Rm, but it puts the result into 2 registers, specified as Rd low and Rd high. Question 4. What reason would there be for using two 32-bit registers to store the product? Consider all possible 32-bit values that we might multiply. The answer is that the product of large 32-bit values will take more than 32 bits to represent. 2 billion times 2 billion, for instance, is 4 quintillion, which takes at least 62 bits to represent. In general, for a product of x bit numbers, you'll need 2 times x bits. To see this more easily, consider what the result will be of multiplying 2 3-digit numbers through decimal numbers, that is. So 999 times 999 is actually equal to 99801, which takes 6 digits, which is twice the number of either of the operands. So why does a mul or MLA use only 32 bits for the result? And because it's designed for small products, which are the most common case. If the product exceeds 32 bits, then mul and mule just drop the upper 32 bits. You, or the compiler, are expected to know when operands are small enough for this not to be a problem and use mul or mule only in that case. Another instruction to look at here, moving on, is SWI, down at the bottom, software interrupt. Now, this is the only instruction we've used in the course but not examined in this topic so far, aside from the coprocessor material that we'll look at in a later lecture. The format for SWI is at the bottom of most tables, labeled software interrupt, and it's probably the simplest of them all. It has fixed bits of 111 and then a software interrupt number. Each interrupt number causes a jump to a different point in the operating system, and thus each system call, roughly, has its own interrupt number. 24 bits leaves ample room for an arbitrary number of system call choices. Okay, we've compared 7 different instruction formats so far, and there are obviously more. When the processor gets a 32-bit instruction from memory, how can it tell what type of instruction it is? Well, if we look closely at the fixed bit patterns, we'll see that it's always possible to distinguish one instruction type from another. Let's try a few. For instance, how do we distinguish an LDR-STR instruction from a data processing instruction? How about a load store multiple function? How do we distinguish it from either of the other two? And then answer the same question for branch and software interrupt. The answer is this is all about the fixed bits after the con field. They are, for instance, 00 for data processing. And for load store single data transfer, they're 01. And they're for load store multiple or block data transfer, 100. And 101 for a branch. And then all 4 ones for a software interrupt. But the 2 multiply formats are a little more complex. They start with 000, 5 zeros, actually 6 zeros, and with 0001, 4 zeros and a 1 for the long. And that distinguishes them from one another. But those 5 bits don't distinguish them from the data processing instructions. Why? Or why not? The answer is that the data processing instruction could have 0, 0, 0, 0, 6 zeros or 4 zeros and a 1 after the con field if its I bit flag here were 0, or if the first bits of the opcode were 0, 0, 0 or just 0, 1. Okay, so then how does the CPU differentiate a mul or mul LL long multiply instruction from a data processing instruction? The fixed 101 bits in positions 1 through 7 seem like a good way to do that, but couldn't the right operand 2 value also have that pattern right in the middle? Why or why not? Consider both the I flag equals 1 case, by the way, and the I flag equals 0 case. The answer is different in each case. Okay, so first, if the I flag is 1, then the operand 2 is a constant, and it could indeed have 1, 0, 0, 1 right in the middle. But if the I flag is 0, then operand 2 is a register in shift value. And per the discussion earlier in this topic, the pattern of bits that has any values and 1s in those positions, this pattern in particular, that's actually not possible. And that's by intentional design. Okay, question 8. If a constant operand 2 could include 1, 0, 0, 1 in the middle, then what distinguishes a data processing instruction with an operand 2, a constant operand 2, a form having 1, 0, 0, 1 in the middle, from a mul or a mul D? Sorry, mul L, a long multiply. And the answer is the I flag will be a 1 if the operand 2 is constant. So the data processing instruction could not have 6 zeros or 5 zeros and a 1 after the CND. So by now it should be clear that the design of these fixed bit patterns is very clever. Fixed bits are dead weight. They don't communicate register numbers, flags, or other data, but they're essential to differentiate one instruction format from another. Very careful design can minimize them without introducing ambiguity. And we'll examine this more closely in the next topic on ISA design theory.